So the title doesn't actually really indicate what we're going to be talking about, because I don't do a lot of talking about modern procedural terrain generation techniques. I'm going to talk a lot about random noise, or like coherent noise, and then I'm going to talk a bit about machine learning as a use for terrain generation. So first, I mean, we're all computer scientists who are interested in game dev, so we probably generally know what procedural generation is. It's algorithmic data generation. You have nothing, you have an algorithm, then you run the algorithm, then you have data. A really, really simple example of this would be if you're like testing a sorting function and you make an array that has a bunch of random numbers in it. That's technically procedural generation. It's just a really simple form of it. You don't really think about it in the same way. But it has a couple characteristics. It's obviously usually going to be computerized. I wouldn't really want to be sitting down at a desk, like writing down a bunch of numbers that I then put into a computer to sort my array. Random generation, obviously, if you have an algorithm that outputs the same thing every time, it's kind of a procedural generation, but it has no variance. It doesn't allow for like testing different cases and whatever. And then it's generally going to be structured data, because why would you just want a bunch of numbers existing in space? You're going to have like an array, or maybe some terrain, or like a dungeon or whatever. I'll try to relate it mostly back to games, since that's what we're talking about. Some examples, like I said, simple testing data, textures, especially in Unity. I don't know if you guys have messed around with the shader graphs, or the what is it, the other graph thing for like animations. The textures are often procedurally generated. Like Unity uses Perlin noise for everything, or not everything, but whenever you have stuff that you don't want to look the same every time. It's also very useful for 3D models. Procedural generation is very common for like mesh generation and stuff. And then for our cases, we're talking about terrain. This is one example of like a texture that was procedurally generated. It looks a lot like clouds. This is actually just Perlin noise, but you can do certain things to it to make it look like something. So obviously video games, so many video games nowadays are using procedural generation, especially indie games. When you have like a small group, a small team of developers, you really don't want to make all the assets yourself. And sometimes you just don't have the ability to. Like, I know for me, I'm no artist. If I'm making a game, I'm going to heavily rely on stuff being generated for me, so I don't have to do the work of art, which is very difficult. Also, for like any game that you want to be expansive, like Minecraft or No Man's Sky, those games heavily utilize procedural generation. Obviously, I think Minecraft made it very popular. Just an infinite world that's just generated randomly every time. It's super cool, makes for a lot of replayability. I think it's something that a lot of people enjoy in games. Also the roguelike genre. Again, I'm not going to explain what roguelikes are, because I think most of us pretty much know, but like Binding of Isaac, Hades, more. There's so many, like Noita. I'm sure I could go for like 5 minutes listing off a bunch of roguelikes, but they heavily utilize procedural generation, because you're going to want to replay a bunch of different runs, so you can get different experience every time. There's like hundreds of items in a lot of these games, and you want to have like not the same thing every time. And that's kind of like the defining feature of that genre, is the procedural generation. Let's see. So now we're going to actually talk about the terrain generation. If you have any questions about like other types of generation, I'm going to try to touch on them a little bit. This presentation is mostly terrain, but I'll cover a few things after. And also, as I'm going through this, if you have any questions about like what's on a slide, or if you want me to go more in depth on something, this is kind of a small percentage of what I have done in research, so I can elaborate more if you want me to. So for the terrain generation, it's just a specific case of procedural generation, and where you're going to use specific terrain representations. There's only a couple that are ever really utilized. There's height maps, which is the very like stereotypical use. You're going to see like a grayscale image with like darker areas represent lower elevation, lighter areas represent higher elevation. There's also voxel representations like Minecraft. You're going to have a 3D grid as opposed to like a 2D grid for the height map, and each of the elements in that 3D grid, each of the voxels, each voxel is basically a cube. It's going to have either terrain or not terrain. And when you're using that voxel representation, it also allows for you to use more data stored in each voxel, so like information about the terrain, which isn't really there in height maps, it just tells you how tall it is. There is one that's not mentioned here that's kind of an intermediary between the two. It's called a layered data representation where you have a 2D array, kind of like a height map, but at each point, instead of just having a height value, you're gonna have another array of like a couple chunks of terrain. So you might have like, at one point you would have like some amount of, I'm just gonna use Minecraft. You would have some amount of bedrock, like some amount of stone and some amount of dirt. And it has an advantage on the voxel representation because you only need like a number to represent how much of this, and a number to represent how much of this, and a number to represent how much of this, as opposed to having like one whole like object at each square. It kind of lessens the memory usage a little bit. A little more in depth on height maps if we want like a super specific definition, which I think most of us probably generally understand this one. You're gonna have XY coordinates or coordinates in a 2D array, and each one is gonna have a height value. This is like a height map from somewhere in Washington. As you can see, it's a grayscale image. We have like the lighter values, like here, this is like the peak of a mountain. Then we have D's, which is like rivers, because the darker areas represent lower terrain. Now, for my implementations, the stuff that I've spent a bit of time on, we're going to look at coherent noise. And for example, like normal just white noise, it's like TB static pretty much, that has no structure to it. We're not going to want to use that for terrain. So we use stuff that's coherent noise or smooth noise. This is an example of Perlin noise, which we probably have heard of before. It's the very common type of coherent noise that's used. I can get more into the implementation of Perlin noise if you want me to, but not in this, it's not in this presentation, but if anyone has any questions about that, I can answer those. So yeah, like I said, that one was Perlin noise, created in 1985, which was like a super long time ago. Which is kind of crazy that it's been around for that long. It was originally used for texture synthesis, like that was the entire purpose of the paper by Ken Perlin that introduced this, was like he was showing that it was usable for different types of textures. I think some of the examples in that paper was like textures on the top of water, or like texturing just some random object. I think he used like faces and whatever. But eventually people kind of figured out this could be used for terrain as well. As we can see, it kind of resembles a height map. I mean, that doesn't really look very realistic, and that's what we're going to get into afterwards. But in some sense, it has a lot more structure than white noise, at least, just purely random noise. And that's kind of the reasoning behind using it for terrain. So yeah, but realism is not always the most important metric. Like I said, it's not realistic, but like we have an example of Minecraft, which uses a pretty simple implementation of Perlin noise. It's not realistic per se, but I mean, Minecraft terrain, it's very stylized, like it works for what it's being used for. And also there's some implementations that will like start with noise and then erode it in some way. It's a really good starting point for if you're doing erosion simulations. It produces some really, really cool results, which I have, I think there's one paper I've cited in here that has an example of that. I'll be able to show you. But to improve the realism of the Perlin noise, we can use fractal noise, which you might have also heard of. I think it's generally what's used in Unity, as opposed to just straight up Perlin noise. Like this is an example of fractal noise. It's Perlin noise with more Perlin noise added on top of it. And like for this one, I just cut it off at a certain height value and just made everything blue, and it looks like clouds. So to get more into fractal noise, it's octaves of noise generated at different resolutions, and that's, now I have a bunch of words that I have to define. So each of these Perlin noise generations is an octave. They're at different resolutions, and basically what that resolution means, this one might be better. When you have your array and you want to generate some Perlin noise, you first have to start with generating a bunch of gradient vectors. Perlin noise is a form of gradient noise. So a gradient is basically the slope, or not really the slope, is in 2 dimensions, it's the derivative of like that location. So it's pretty much telling which way is the slope going up. And the resolution is how many gradients you generate. So at resolution 4, it would start with like one there, one there. Oh no. Very good. Basically, it has 5 logically, but it's kind of, you have 4 regions that you're doing on each axis. So that's why it's called the resolution 4. It's because you have like 4 boxes where it's being generated, and you're gonna have gradients on each of the corners of all those boxes, and then all the implementation, it does a bunch of height interpolation stuff, which is kind of cool, but I probably don't have time to get into, unless you really want to. But essentially, those are the resolutions, and the octaves are then added together, but they're not purely just like added one on top of another, because that, well, I can show you, it produces something interesting, but this is not all of them added together just at their full values. Each subsequent octave beyond the first one is multiplied by a scalar, which kind of reduces its influence. So for example, if I were to do some fractal noise or generate some fractal noise, I would start with that first one of resolution 4. Then I would take the resolution 8 image, multiply it by 0.5 maybe, and then add it on top. So it's like, it won't create super granular texturing, it'll kind of smooth out over time. And this is what it looks like in practice. And also in 3 dimensions, we can see it kind of looks like some mountains and valleys. It's starting to resemble terrain more than basic Perlin noise would. And this is what I was just saying with some math notation about how the octaves, when they're added together, are not purely just added at their full value. You usually use something called persistence, which is basically a variable that tells you what to multiply the scaling by at each subsequent step. So if I had a persistence of like 0.5, I would start out with multiplying the first octave by 1, the second one by 0.5, the next one by 0.25, and by 0.125, and so on, depending on how many octaves you use, which you could use a lot, but when you get kind of beyond using 4 or 5, they're already going to be adding very, very little influence to the output and won't change it much. And that's just more complexity that you're adding, so it would take longer and longer. I will note there's one more variable used in the generation of fractal noise. It's called lacunarity, and that's basically what you multiply the resolution by at each step. So an example with these would be a lacunarity of 2, because I start with 4, then I go to 8, then I go to 16, and so on. It's when fractal noise is actually generated, it's almost always like multiplied by 2. The resolution is multiplied by 2 at each step. It's pretty standard. Same with the scaling being multiplied by 1/2. And here's an example of not using persistence versus using persistence. As we can see, this one on the left, it's very textured, which may be useful, but you end up with a lot of like unrealistic like ups and downs in your terrain, which is why you want to multiply the subsequent octaves by a smaller scalar to retain kind of the smoothness of the other one. And oh yeah, for reference, this right here is what was used to generate that texture of clouds that I showed before. I pretty much took like, it goes from 0 to 1, and I pretty much just took everything below 0.2 and made it blue, and then left the rest, and then we end up with something like this, which is pretty cool. And there is more that we can do besides just using fractal noise. This is a lot of the work that I was doing, which is kind of messing around with how the Perlin noise is generated. You can kind of apply functions to the Perlin noise to change what it looks like. For example, this one, I started with the Perlin noise height map on the left, and then I took every number or every value in that 2-dimensional array, raised it to the 6th power, and then took the square root. This will make a little more sense when I cover something like the next slide where I was using absolute value. But it creates essentially, it's kind of hard to tell, it created really big valleys all over this height map. So we were left with only a couple points that are higher up. And we can kind of see that like this corresponds to a point that was already high up over here. So then with something like that, we can take it, add fractal noise on top of it, and end up with something that kind of looks like islands, like an ocean. I could change the color of this to transition from like blue to green or something, and it would show it a little better, but I think this kind of gets the idea across. Here's another one. This is kind of the first step of what this was. This is Perlin noise with a absolute value function applied. And essentially how that affects the Perlin noise. Oh, I guess I should say this is not actually an absolute value function, it's a negative absolute value function, which is just kind of, obviously it's the opposite of the other one. And I can get into why that happens. But it creates a bunch of like ridge lines, and that kind of resembles mountains a little more than we might see. Obviously, this one on its own is not a very realistic like set of mountains, but we can then do the same thing with fractal noise and end up with a terrain that, although it's a lot of mountains all consolidated in one place, kind of resembles some mountain ranges and peaks better than you would see with just the normal fractal noise that has some lumpy areas. There's another process that I worked with, which is kind of simulating erosion, not really, but it's scaling the next octave that you add based on the current one. So for example, we start with this one, which would be the first generation of noise that we want, and then normally we would just add the next octave. But what I did here, instead of just adding that octave, I took it and I multiplied it by the first one, resulting in this. And essentially what that did, all the values that are really low on the first one, like close to 0, when I multiply the second one by that, the values in the second map are going to go down significantly. So all of the low terrain areas in the original map are not going to gain much elevation when you add another generation of noise on top of that. But conversely, when you have the high elevation, it's going to leave this new map with like the full effect of what it normally would have been adding. And over a couple of steps, we end up with something like this. We can see that it kind of represents like, it gives more variation in height, like the original fractal noise. If I go back to it, we would see it's kind of, there's not really like one area of high elevation that kind of tapers off. We just have a bunch of like high elevation areas. But when we use this scaling based on the values, we have kind of a more large scale structure for our terrain, which can be seen. We have like one area right here, which is like a higher mountain, and then maybe these, instead of just being more mountains of the same height, are a bit lower, like hills even. And then we have more like larger areas of low terrain. And we can then combine multiple methods. So this, I took this one, and instead of just doing normal fractal noise, I added this scaling to it. So I used both of them at the same time, and it yields, it's still pretty similar to the first like peaky one we saw before, but it is distinct a bit, as in those like the low areas stay relatively smoother compared to the high ones with all of their like variants. Now, some benefits of using fractal noise or Perlin noise versus other terrain generation techniques, and I'll compare this mainly to erosion simulations. Tileability, seedability, and they're fast. Basically, what tileability and seedability kind of go together. It's how Minecraft doesn't generate like the entire world all at once and try to store that in memory, because that would not work. It generates like one chunk at a time, and with how Perlin noise works, you pass in a random seed to the random number generator, and it is continuous across the entire domain, so for like all numbers. And that allows you to, with the same seed, generate one chunk, then generate another chunk, and they will always stay connected, because it doesn't like, it basically is continuous between chunks. You give like X and Y values when you're generating Perlin noise value. I guess, yeah, I can give a better example of that. When you're generating a normal Perlin noise height map, you generate one value at a time, and you pass in an X and a Y value to where you're trying to generate. And when you expand that beyond like just one chunk that you're generating, it will, like, you're still using the same gradients, basically. So I guess, yeah, I can show you with this. So say this is all we wanted to generate, like this is one chunk. When I generate something over here, these two gradients are the same, so it's going to remain continuous between the two regions. And it's much faster than erosion simulations. For those, you need to simulate like thousands of iterations of erosion. And also, when you have an erosion simulation, you have to start with like your full height map and erode that, and that's not going to remain continuous between regions. So you would have to have your whole world generated all at once, which is very memory intensive and not really very useful. But fractal noise, it's kind of cool. It's still very far off a real height map. Like this is an example of some mountains somewhere. I think it's in like Colorado or whatever. And that's the fractal noise. Like these are pretty far off. This isn't, it's doing better than Perlin noise in terms of realism, but we're not super realistic yet. So I'm going to give an example of a couple modern methods that are more realistic. They're not limited to using noise functions. It's very often, at least in the modern days, erosion simulations or machine learning. People do a bunch of different types of erosion simulations. It's really hard to simulate multiple types of erosion at the same time. So a lot of papers will like focus on one or another, or maybe getting like a structure set up for erosion to be simulated. They also use a lot of real terrain data, mostly for machine learning. It's kind of not necessarily useless, but not as important for erosion simulations. Noise function post-processing, which is basically like starting with the noise function, doing something to it. It's essentially what I was doing before. And then also something pretty common, at least in the video game space, is you start with a procedurally generated world, then you have your visual artist come in and mess around with that until it's exactly what the designers want. And that's another good way to do it, but doesn't really work if you want to continuously generate terrain. So here's one example of a paper that did erosion simulation. They simulated glacial erosion. And as we can see, this is like super realistic, or at least I think so. Like this very well represents what type of mountain ranges we might see in real life. And they started with a noise-based terrain. So they generated fractal noise, then simulated erosion on it, and we end up with something super realistic. Other ones, machine learning. This is one that I found pretty cool. They trained two models. One model they trained to generate satellite images. So they just gave it a bunch of satellite images, trained the CNN, then have it generate random satellite images. And then they trained another one to look at satellite images and create a DEM, which is just the height map. So they have one generator that makes some random satellite images and another machine learning model that looks at those generated satellite images and creates a height map from it. So what we can end up with when we combine these two is a procedurally generated height map that is also fully textured, because you just add the two together. There's also some methods using real data, which are not using machine learning or erosion simulations. These are two papers from quite a while ago that I found pretty interesting. This first one here with the half-life symbol, they were taking, and this was made in 2007. They were taking real terrain data and doing some feature extraction from it. So essentially like having some sort of just programmatically looking at it and saying like, oh, here's like mountain ranges or here's rivers, basically just looking at what the features are of that terrain and then kind of copying that over to an image that's passed in. So for example, this is the input image and this is the input height map and this is the output. What the program essentially did was look at this mountainous area, extract the features of the mountains from it and paste those features onto this drawing. And it yields some really cool results. This other one was using something similar to Perlin noise. It's called value noise. Instead of gradients being at each of these points, it's just a number. Like a random number, except instead of making the numbers completely random, they were pulled from a real height distribution. So we end up in that scenario with terrain that kind of resembles a real terrain because it has real height distributions in it, and it'll still be relatively different from the actual terrain. And now This is the paper that I reproduced for my thesis. It uses style transfer, which I'll explain in a minute. They use style transfer for terrain generation. And what is style transfer? This is essentially a very high level idea. You have one image, which is your content. You have one image, which is your style. You feed both of them into the style transfer model, and it produces a new image that looks like the content in the style of the style, I guess. So like passing this image of the turtle, say I want this turtle to look like these waves, and now you have a turtle that looks like waves. It utilizes a pre-trained network that I would not have been able to train an image classification network for this. That's way too much. But thankfully there's plenty out there that already do the job well enough. And as shown in that paper, we can pretty much do the same thing with height maps and noise. We don't need like real images. So here's some important things to know about style transfer. We give it two images, we give it content and style. The content for our purposes is going to be the noise, and the style is going to be a real height map. They're each given a weight, and in the implementation for this style transfer, it is a little weird. The weight for the content is like 1, and the weight for the style is like 10 million. So the style is given much more influence over the resulting image than the content is, and we'll see what that is in a minute. So here in practice, we have the style, the height map, and the content, the noise image. And when we combine these using the style transfer, we end up with something like this. It would have been nice to have them all side by side, but I'll just go back and forth a couple times. We can see this has a lot of the features of that real height map, but if you look closely, you see it has essentially the same shape as this noise image. And this was entirely procedurally generated. It is not quite as fast as like noise functions. I think generating one of these, I can demonstrate for you guys in a minute too. It takes like 10 to 15 seconds just for this. So it's not super efficient unless you just want like one region, then it's all right. And here's what it looks like in 3D. This is like so much better than all the fractal noise we saw before. Like to me, this kind of looks like a place that I'd go hiking or something. It's pretty cool. And now what I did beyond just re-implementing the style transfer is I went to alter those output height maps to kind of make them more, I mean, it already looks very realistic, but obviously the world is not covered in mountains everywhere. So we kind of want some more variation in what types of terrains we see, like mountains versus plains versus hills, valleys, deserts, all that stuff. So first thing I did, as you might be able to see in this, some of it is a bit noisy. Like there's a bunch of jagged areas, and that's not super realistic. So what we might want to do is blur it a little bit to get rid of that noise. We can see this second height map here is blurrier than the first one. I used a Gaussian blur, which is basically, it's used for images. It just pretty much takes an image and blurs the features. It has some other uses, or some pretty interesting uses, but I wasn't going super in depth with that. So for example, maybe we don't want a world entirely covered in mountains, so we can scale down our height map. This is the same height map that I had just shown you before, but some of the regions are scaled down, and now we have like 1, maybe 2 sets of mountains, with the rest of it kind of being much more subdued, much lower, kind of like plains and hills. I can, let's see, yeah, I can tell you about how I scaled that down next. Oh, yeah, okay. So that is the end of the presentation. I can tell you a little bit about how I did this scaling. I utilized, is there an eraser? I utilized Gaussian blur again for scaling down these height maps. Basically, what I did, I generated, oh wait, I have a much better way to show this. So that's the end of the presentation. So I'm going to get a lot more informal now. Basically, here we go. So I have my height map, and here's, it's kind of like the K nearest neighbor. I basically just made boxes with different height values. And what I did, I took that and then I blurred it to get this. And when this is multiplied by a height map, you end up with that same height map that's kind of rescaled. So like this whole region becomes lower elevation than it was. This kind of remains the same, because again, this is scaled from like 0 to 1. And like this is kind of somewhere in the middle, so it gives us more of an effect of varied terrain, so the world isn't entirely covered in mountains. Yeah, I guess there's also something very similar to that. This kind of looks like a river, and that's what it's supposed to look like. I can take something like this, multiply it by that same height map, and then now all of a sudden that height map has a river running straight through the middle of it. And since I'm just multiplying by the values that are already existing, it retains all the realistic features that it had originally, and now it's just added in some more variation. Ideally, you can do like a combination of these two things. You end up with very varied terrain in a small region with only like one actual generation, and like making this river and like making this, they're both super fast. So the only big like brunt of the work is done by the actual generation. I guess we can do an example really quick. Doesn't take too long to generate. Oh, and I guess I should say, so one interesting thing for style transfer, you're generally giving it like RGB images, so they're gonna have 3 channels. Height maps don't, it's black and white. So each of the like the noise and the actual height map are both passed in normally, but then the output would be in RGB, but we don't care about that. And in practice, the R, the G, the B, the 3 channels of the output are all very close to each other, so I just averaged 3 of them and use that as the resulting height map. And you can see it's almost done running. It's only going slow because this is the first time I've ran this today. But there we go. Random height map generated from I guess I can show. Okay, so it was this noise and that terrain, and it generated this height map. And that's pretty much like bulk what I've done. I can, like, here's an example of what it looks like when you have the river added to it. Okay. Whoops. I guess I can't show that right now. I do have an example somewhere. But I am pretty much done, so if anyone has any questions, now would be a good time. Let's see. Here we go. 3D map that I added a river to. Pretty much similar to the rest of the stuff. It looks a little weird because the river is like scaled way down. I took it from like -1 to 1 with the river being at -1, so it scales the values a little weird. And we can see like, here's what we had before, and then I added the river to it, and we get that. Pretty much it. Oh, I guess I was going to show some more different things about procedural generation. We don't only care about terrain generally. One really common thing is generating dungeons. And none of this is work that I've done. This is stuff other people have done. But for example, procedural generation, you randomly place down a bunch of rooms, and then you decide some way to connect them. And then you have a procedurally generated dungeon that you can then add assets to, and you have something pretty cool there. You can even extend this into 3D, which yields a it's very complicated, at least just from looking at it. But this is like, I don't know, it's completely procedurally generated. Then you just add assets to it. There's something else that is pretty interesting called wave function collapse. If anyone's heard of that, it's essentially, let's see, what's the best way to describe it? Essentially, you're given a set of like prefabs, and each of those prefabs have a rule of what other prefabs it can be next to. And then you have an empty array. You place one down, and then you just keep placing them, and you limit what can be placed next to something that already exists by those rules. So, I don't know, for like a very vague example, you would have like, you want to generate like land with beach and water. You have these like land tiles, and they can only be adjacent to beach tiles, and the beach tiles can only be adjacent to water tiles. So that if you place a land tile down somewhere next to it, you're only going to get another land tile or a beach tile. You're not going to get water. So then you end up with something that might look like beach with water next to it. In practice, something like that would probably just look like a bunch of brain pixels. But like the way the wave function collapse works, essentially you give it something to base all this information off of, then just generate something randomly based on the rules that it can extrapolate from the image you give it. So like this top row here, this image of some buildings is passed in. All of these are procedurally generated based on the rules that can be gathered by looking at this. And it's all done programmatically. You can change how big of an area the algorithm will look in to decide what the rules would be. Yeah, and it creates a lot of really cool emergent behavior, like being passed in just this little image of a weird S can create some really interesting things that don't necessarily look exactly like the original. I think that's. Here's just like another dungeon generator. It does something very similar. Yeah, that's pretty much it for everything I know about procedural generation. Any questions? Any like additions? Something I'm forgetting about? All right. Well done.
But I thought it'd be cool to follow this up with a little bit of a discussion about how this actually has been applied in video games. Something like, there are a few different ways that this has been done in practice. A lot of games like Minecraft, Valheim, off the top of my mind, have certain biomes that are associated with different terrain generation rules, and others like more like No Man's Sky would be more like there's not so much variation in it, but the actual moment-to-moment variation is more extreme. It doesn't look as realistic, but it feels like you're actually exploring a large cave network or planet. Yeah.
Those big infinite type games where the generation keeps going.
Yeah.
How would they give it first spot of the land was generated? How would they put the next spot next to it? Remember what the previous, like how do you remember like where mountain like should go quickly through?
Yeah.
Let this plug in because I actually have an example.
Yeah.
For something like Perlin noise, it's you give it a seed, so it becomes deterministic. And the way that's done in practice is you would have, I think the base implementation of Perlin noise has like a, what would it be? It has what a permutation table. So whenever you look at a specific point, it's always going to be next to the same gradients. The way I did it was a little bit different, based on the X and Y value that is like where that gradient, where that value is supposed to be. I take those X and Y values, concatenate them to get a number, then use that number as a seed to generate the whatever would be at that point. So it'll always be the same gradient at like one point at 0, 0, for instance. And that's how it's generally done for something like Minecraft or No Man's Sky, at least with the noise functions. Beyond that, it probably varies a lot. Like Chris mentioned terrain stitching, that's one thing that could potentially be done. If you have two non-continuous height maps next to each other, you might want to mathematically calculate what the intersection between the two would be and use that. That's something I would want to do for my thesis, but maybe limited by time on that one.
Something like that, yeah.
No, this is just weird.
Yeah, so we talked about pending new noises on top of them, like
Yeah.
the Your River example.
Mhm.
So say in Minecraft, I was to go in game and build my own mountain. Just on blocks.
Yeah.
Would that change the seed?
No, when you add stuff, the seed only kind of determines what is generated when you load a chunk for the first time, then it's just there and it's stored in memory. And when you add stuff, like it changes the values in that chunk, but it doesn't change the seed that generated the chunk. Because each chunk in Minecraft only has to be generated once.
Yeah, you kind of store it off in your own save file about what changes you made to that. If you pass that seed on to someone else and have them generate it, they would generate the changes that you
Yeah, you
made.
tell things.
Exactly, they would be able to do whatever they wanted to do with that generation, and not.
Yeah.
Great question.
Please ignore my instance like this code, it's not great. Or it doesn't look good, so here, to better answer your question about how it like knows, when I want to get a vector at one of the points to generate the Perlin noise, it is always going to be the same, because I passed in the X and Y value of where this pre-generated vector is supposed to be, and then I create the new seed. From that, it's deterministic because it's always, the X and Y are always gonna be the same for the same points. And then I generate a random vector based on that, but since I'm using the same seed every time, it's always gonna generate the same one.
Okay.
I think a better implementation is using the permutation table, but that causes your terrain to repeat every however many blocks or however many pixels, because it depends on how big your permutation table is. If you have one of like 512 values, every 512 units, your noise would repeat, and you might not want that. Anything else? Other questions or thoughts?
There's one part that really interested me was when they took just the lambda symbol and added the actual, real map data of a real location and then map that on. Was that basically the inspiration for how you got to sort of the generation of taking the river and then adding that onto your already existing?
Kind of, the way I got to that point with like adding the rivers, I was essentially trying to say, hey, I want to generate mountains, and I want to generate hills, and I want to generate plains. I want varied terrain. And in doing that, I realized that like, if I take one mountain or one height map of just mountains, and I kind of make a, and that's where I got the idea for this thing. Essentially, if I take like half of it at 1, half of it at 0, blur it so it's smooth in between, then I have mountains and I have plains. And that, I originally wanted to take like 2 separate height maps and mathematically stitch them together, like generate the in-between area, but this ended up being so much faster and easier that I ended up just using that. And then I just kind of expanded upon it. I was like, oh, hey, this like, I can kind of create a river doing this if I just like make a river shape and paste the height map on top of that. And I guess I did want to mention, because someone said something about No Man's Sky as well, something interesting done with that is No Man's Sky, since the game isn't different for everyone, it's the same for everyone. So they use one seed to generate all of the game and then just ship that out to everyone. So everyone's kind of exploring the same infinite universe, which is kind of.
Although they didn't generate all of it, right? They generated the rules
For
for
it,
generating
yes,
all
they
of it.
generated the rules.
It's the key for that, but there are certainly,
You don't have the.
there are planets that haven't actually been generated. Yes, that are being generated on the fly as players are entering that system for the first time.
It's not the limit of there is a limit to the universe, it's the size of their server.
Well, not really.
Yeah, it's not actually
It
stored.
doesn't have to.
Yeah,
It would essentially be infinite, like you can go anywhere and it still has the rules for generation, so you're gonna find something, no matter where you go.
If the servers get too full, they can just discard already generated planets. But then since it's a deterministic generation process, they can just regenerate that planet and it'll be the exact same later.
Yeah,
My base and everything I have, has gone there.
Well, no, your base is stored locally on the save file on your computer.
Yeah.
The server just generate like the base planet, so when the server discards it, your computer, and then it has to generate it again. Your computer just has to reapply your base changes to that.
so for example, there's games like old games that people have made that when memory constraints were actually an issue for game developers. There's a game made by some like people in Germany back in like 2007 that I think the game itself is on like a 200 kilobyte executable, and then when you run it, it creates like gigabytes of textures and assets because the rules for generation were all put in the small executables and the game kind of generates when you load it. So all that stuff isn't stored somewhere, it's made on the fly, and that's what's useful about procedural generation, is you don't have to store assets because they're deterministically generated.
Yeah, the same for the old other books, like there's Arena and Daggerfall, it's very similar ideas, to be able to generate massive worlds with significant restrictions.
Yeah, that's essentially how any game ever has an expansive world that seems too big to be true. They didn't make it all themselves. In most instances. I think you have something like whichever Elder Scrolls game it was that was like in the Scottish Isles or whatever, they had the entire thing in the game, which is kind of pretty like sure.
The only one that takes place on actual Marvel.
I think it's that one, yes. I don't know that.
Scottish, well, there's a massive volcano, so I don't know how Scottish they could done it all.
Scottish S. Being based on that.
Any other questions for Hunter about any of the work that he's done or anything that's floating around in your mind for how you would utilize any of these tools to create something that you're familiar with or interested in?
And for procedural generation expands beyond just like textures or assets, like Borderlands, for instance. All the weapons in Borderlands are procedurally generated, so you have like thousands of different potential things that you would find, but it's different every time you like find something. It doesn't have to be hard coded. Same with like Path of Exile or any ARPG. They have the confines for what stats can be placed on a weapon or what weapons can be dropped. But in the process of playing the game, you're not going to be seeing the same stuff as someone else because it's all still done randomly. That allows for a lot of new strategy, replayability. Like it does a lot for a game to have randomness. But I don't think that's really. I think like a couple of the games made for a game, like the first set of games used procedural generation as well in some form. Probably most of them.
A lot of them. Elementary procedural generation, just because of the constraints of hardware at the time.
Yeah, I mean, even Left 4 Dead had procedural generation on any small numbers, that as well.
Yeah, that's another example. You could define anything that's done randomly in a game as procedural generation in some sense. Usually it doesn't match up very well, like with random enemy spawning. It's kind of procedural generation, but at that point, it's not really structured, so you're not utilizing the generation beyond just throwing something somewhere.
There's a middle point somewhere where if it's basic enough, it's randomization, but as soon as you throw in enough constraints, or there's a certain number of constraints that allow it to be procedurally generated, where you start to relax those constraints and just say, make these decisions for me and make them make sense, given the constraints of we want realistic looking terrain.
I guess constraints would be a good way to kind of quantify it. It's like randomness with constraints generally leads to procedural generation. It also lines up very well with just emergent behavior in games or just in things in general. Like, I don't know if anyone's heard of Conway's Game of Life. That's a really good example of a couple, especially in confinement.
I haven't, but there's some overlap with those who are in compliance.
You have a couple of very simple rules which lead to very complex behavior in practice.
And it's undecidable because again.
But I don't know if it's undecidable, but it is Turing complete. Like
The fate of a pattern is undecidable.
Yeah.
Oh, yeah.
Whether or not it reaches a stable state or
That's
not.
that's true. Because it is also Turing complete. You can make the computer in Conway's Game of Life.
Yes.
And people have done that.
Play complex like.
Yes, you can make Conway's Game of Life in Conway's Game of Life.
Turn.
Well, I'm sure Conway's Game of Life.
For those of you who haven't seen it, it's really cool.
Oh, this is an awful UI. So here's a couple pixels on a graph. Basically, the way this works, you have a grid and each grid cell contains either something or nothing. And there's rules that determine what happens over time. Which iterates step by step. Can I draw on this? Should be able to just click, yeah. So if I'm able to add a bunch of stuff, I don't know what's gonna happen, but something's gonna happen. Yeah, and then it just goes away. So it reached a end state, but we can't have known that would happen.
In general.
Yeah.
Cool.
That's all. Procedural generation is really cool. There's a reason I spent the last 6 months learning.
What I think is there are a lot of uses for procedural generation, especially in games that have not really been explored. That's why I think No Man's Sky is a cool idea, is it's really on the cutting edge of what we can do. And even if it was. We were kind of lied to about what that was gonna look like when it was shipped, but a lot of the research has come out of the fact that that game exists. And all of that effort and work went into it, I think, has led to kind of a new renaissance of procedural gaming.
And also indie devs becoming more prominent. I think like every popular indie game as of late is utilizing procedural generation in some way.
Especially when you struggle with drawing.
Yes, especially when roguelikes are as popular as they are.
I mean, it's not everyone, Palatro and Deltarune come to mind,
Well, that use user
that don't use procedural generation.
Well, I mean, Ultra, you put in a seed for your run.
That's fair.
It's deterministic, like the run itself is random. It doesn't use like really structured procedural generation. At that point, it is more just randomness. But I don't know, one could overdo, but I won't.
Yeah, all right, let's thank Hunter for this time and.
About procedural generation or want to use it in your games, just like message me, I can try to help. Or if you just want a random pipe for your game, I can send you.
Yeah, feel free to utilize any of the tools that he's created, maybe you can embed them somewhere in your game, that would be cool. All right. Anything else?
Good luck with getting to. Can't wait to see them.
Yeah, I did kind of want to follow this up with a discussion though about the issues. Can we just get a show of hands, who's played games that have utilized some kind of procedural, either terrain generation or something that you could think of as reasonably procedurally generated? It's basically everyone. So.
Has anybody in here not played Minecraft?
Yeah.
I don't think this is a single CS major who has it.
So what are the issues with procedural generation? When you play these kinds of games, what do you wish was there that isn't, regardless of whether it's possible or not? What are the downsides of using it, and what are the, how do I want to state it, just the trade-offs that you have to experience in order to get that procedural generation in its current iteration?
I guess a big drawback of all procedural is pure customization. It's really hard to do.
Yeah, the user has to be responsible for the customization. It's not so much the game as much. It creates places where maybe there's some excellent base building inside of this, but it relies on your ability to create the base, not the game's ability to create different bases
Right.
that exist, because that's many more constraints in the game.
It wasn't just that, because there was stuff I wanted to generate for myself in my, I'd love to have sort of this environment around here and this around that. Like a starting spawn where specifically I see certain customized asset that can spawn in the location, and then from there it starts to generate more random.
Sure, yeah, or user control over it.
Yeah, I know there's quite a bit that asks for that.
Let's go Leo in the back and then 2 and then 3.
You get, without a better word for it, screwed by the system where you like. It generated in and you can't find the things that you want to find because they're so far.
Based on the seed, no one's going through on each seed and saying, is this creating a relatively equal experience for the players who spawn into this particular seed? you can get a seed where maybe there's a random boss location that is part of that, and it just ends up being either so far away, or maybe it's close, but it's on another continent that you can't get to. If there aren't enough rules for how that is generated, then you can have very different play experiences.
Yeah, that is Valheim.
Yeah, I'm actually using it, that was the game that was in my mind as I was thinking of
Looking
that
at
idea.
the maps, all the way out in Timbuktu.
Yeah. So you can imagine as a developer, if you're utilizing procedural generation, it is your responsibility to come up with and think of the constraints that you need to put in place for the procedural generation, so that the players have a relatively even experience. If there is a competitive nature to your game, then it's especially important that players' experiences are reasonably similar, and that the variation there doesn't give one player a significant advantage or completely ruin a run or someone's experience with the game.
It's really easy to accidentally make procedural generation just really boring. If you don't have enough, it's just variety in there, it can just end up being like, I'm going to all these different places and they're all different, but they don't really feel different.
Right.
They all feel the same. Yes, I have played Starfield, how did you know?
How can you imagine working through that? If you're a developer of a game that's utilizing that, what do you prioritize in order to create really different experiences from the player's perspective? Any ideas? What would you focus on?
Like for like Minecraft, well, places are different, but each environment has different things, like for materials, like you don't get that environment, different like monsters.
Yeah, so we've kind of reached a stable state where biomes have become how games differentiate from areas that feel very different. If you start out in a forest and you go to a plains and you go to an ocean, you go to a mountain, you go to a desert, each of those would have different enemies and different rules for how trees are generated, for how water is flowing, for how anything else about that area. How would we get away from that? That's something that I've kind of been passively thinking about, but haven't really applied too much thinking to. Is biomes are great, but it's not really how the world works at a small level. Games you go from one biome to another, but you don't just instantly go from mountains to a desert anywhere particularly quickly. It's immediately where one just stops and one starts. How do you start to lead that together and or create more realistic experiences that represent more realistic terrain? Or is the concept of biomes as good as we're going to get? Are there any reasonable improvements over that?
What you talk about kind of just sounds like stitching between two biomes, and then making gradient between them, because you can technically go from a mountain straight to a desert. It's called the Himalayas, and then the Gobi Desert because of the
Yes.
rain shadow.
Yeah, that can happen, but it's rare, or it's somewhere that's once in the world, and other places are different. That's kind of a meta-analysis of from the top down. Where are the biomes, to what extent? It's not so much binary, this biome or that biome, but how much of each biome. Yeah,
I just wanted to say, I feel like if you're looking for realistic, it's kind of hard for different developers to make games that big, but also
Right.
content so filled.
right.
You
There's
know?
a huge trade-off between randomly generating something and really putting the effort and time into placing the experience that the player is going to experience. How do you abstract that into an algorithm that still creates that level of engagement and progression without the human touch? I think that's really going to be the next step forward in gaming, is if we can find a way to procedurally generate that. How can we use generative AI to not just generate terrain, but now start to generate experiences? How do we tie together large language models and terrain generation to now create a large scale explorable world that feels more alive? 1, 2.
I mean, if you look at the actual climate of their. How would we generate that? Because that's how we have a lot of the stuff we have now. Falling first off, the giant ball in space for spinning in with this angle to the sun and the distance from the sun, because now we're kind of moving back up to a no man's sky perspective of, well, now we're generating a planet, so then how do we scale it back down with all these other factors that affect this single spot in the game?
Yeah, so maybe doing something like simulating a more fortress type of history, but now it's the planet's evolution rather than just the history of events and people and everything else that Dwarf Fortress generates. It's a lot, but you could apply kind of similar rules to that, to aging of a planet, and you get something that might be a little bit more realistic. Interesting.
So my problem with like, games like Valheim that use procedural generation is biomes start feeling very samey.
Yes.
Like I would not be going to the sixth swamp I went to because I'm just looking for iron and then, you know, every swamp is the same, the positions of the dungeons might be different.
Right.
But I would think that like you would use like microbiomes within that biome to kind of create that experience of differentness between the same biomes.
Okay.
And I don't think that Valheim does.
Yeah, so you have kind of a,
This is the same swamp I ran through. You know, you could drop me off in any random swamp, and it would be the same experience.
yeah, maybe you have different seeds that are different levels of, there are biomes, but then there are climates within those biomes, and then you mesh those together and you get a more humid swamp, you get a more dry swamp, you get a more, yeah, you can start to make them feel different based on some other input parameters that aren't just what the biome is.
Yeah.
Then you could add some gameplay relevance to climate, and now when you combine biome plus climate, you get a different experience that really rewards that exploration. As a player goes, everything they find is new in some capacity.
Yeah.
Yeah, I think that is an excellent direction to go. Any other thoughts?
Back to biomes, and now we're just subdividing the biome.
Yeah, you said kind of multi-dimension, instead of having a single list of biomes, now you make a second dimension or a third dimension or a fourth dimension to add complexity to that. But as you add those dimensions, you now have to think about what are the gameplay outcomes from each of those dimensions? What decisions are players making? How is the progression found through that multi-dimensional space rather than just, we want them to experience this biome, then this biome, then this biome. That's a very linear progression. What does a two-dimensional space look like? What does progression through a two-dimensional space look like? What does progression through a three-dimensional space look like? I think that's where game design should go. So the question is just, who's thinking along those lines? How do you create that and still make meaningful player decisions, interactions, progression?
Or how we don't become versions.
Other thoughts? I just thought this would be a fun discussion to have after that, because it is really relevant to the modern cutting edge of games. And if we want to make the next good change in games, I think it's utilizing a lot of what Hunter just talked about to apply that in ways that haven't been done. At least within the exploration genre, within anything that we could utilize procedural generation for, which is more than just terrain. As we mentioned, Borderlands uses that for weapons. Any other ideas of what we could use procedural generation for in a way that could feel interesting or relevant? That is one of the things that Borderlands did so well, is the first time it really felt like every gun was different. There were RPGs before that generated random weapons. Diablo 2 generated random stats on weapons, but they required a certain base, and it didn't really feel like they had as much depth as the guns in Borderlands did. What are other outcomes in games that could be procedurally generated, assuming that we had an intelligent generation algorithm?
It would probably be possible to generate like randomized events.
Randomized enemies, yeah,
The game would run, I don't know how long it is. Pretty looking at this final score, that you build features.
yeah.
And stay up dynamic. Set up animations, so you figure out the latent block and try to have you move buildings around.
Yeah,
If we had an algorithm to create creatures like
that. Katie Taylor comes to mind as an example of you're doing that for yourself, but also the world's generated around you. In those kinds of I think that's a step forward from SCORE, but I'm gonna step back graphically, but a step forward in terms of the actual use of procedural generation.
I'm just walking.
Procedurally, you're generating new entities types from sort of like genetic algorithm.
Yeah,
Say we cross-spread entities, what does that look like? Is this a pure abomination? Will this be terrible for what advantages does it add, things like that?
cross a great work with a Leviathan, and you get a great. That's why there are so many.
No, they can. I know. They might.
I'm just trying to mind here, and I took that first.
Yeah. So yeah, I think enemies is a great idea. I've been thinking that procedurally generating story could be really interesting, but also incredibly difficult to be able to create some kind of emotional meaning. But if we had a better understanding of story, then we could start to create this concept of the way that roguelikes gameplay is different on every run. What if your path through a story-driven game was different, and not just because you made different decisions that forked the story in ways the developers intended, but it evolved based on some parameters based on the decisions that you were making, that created different decisions to make, that created, this is way out there in the future, I feel like, but it's something that could be really interesting if it was done well, but also incredibly difficult to do well. How could you procedurally generate? What else?
Yeah.
Yeah, I think in terms of story, the hardest thing to do. The most possible thing is to be completely procedurally generated the story, as in the story purely written.
Right.
Then it's a lot harder, but however, I think a better approach is to have. Story beats or sites are see a lot more generated than that's then you have a lot more versions, like say, I get a pet in this run, I die this pet for the next run, but then the pet dies tragically in the middle of the game, that's an emotional moment that could not have been slain.
Right. So the emergent outcomes are randomly generated. I like to think of something like a Ringworld or Dwarf Fortress type of run, where based on the random events that happen, the emergent narrative of this randomly generated couple that has been together for a while now tragically loses one of those members, and how does the other person that survives this cope with the change? So you can absolutely use random events to create emergent narrative that isn't necessarily told to you, the player, but might come to pass through the use of those game mechanics, where you could create story based on the events that happen as the player. So I think that's also an unrealized space that could be explored in more detail. Yeah, just a bunch of ideas, but I think that leads to a whole. We have a whole class in just that of what would it be like to make progress in any of those areas, but. That's what I think the future of games will look like. Using technology to create emergent behavior, emergent outcomes. Okay, I think I'm gonna pause the recording. I don't know if this is gonna be the end of it or not yet, but my plan is to hand back some exams, go over any questions that we have on exams, and then as there is time at the end, possibly go back to some reinforcement learning, or maybe we end with just a little bit of time to work on some games. So that's where we're going for the moment. Goodbye to people watching this back.